Thank you very much, and thank you all for coming. It's a nice, intimate little space that we've got here as well, which is really quite nice. So I've got quite a few screens on here. I've got OBS, so it's going to take me a little while to juggle between the different views. I've got a number of different views happening, so if I stop for a second, please bear with me. So just a little bit about me to start off with. As Jonathan said, I'm one of the technical directors here at IOActive. I focus on secure engineering, so I'm very much on the left-hand side of the manufacturing V, very much around helping specify requirements and test cases and actually engineering products securely, but also helping clients process the results from a penetration test, what that actually means from an engineering point of view and how to apply remediation to their overall product development lifecycle. I come from a research and development background, so I'm very much engineering focused, and I do love to talk about the various patents that I've got. They're all very, as you can see, a secure RF protocol that intrinsically binds time of flight and data transmission, so they can't be separated. So it's an authentication protocol so that you can't relay, replay, etc. Other fun things, again, around signal processing, an agentless monitoring system for aberrant behavior detection in macro scale machine learning systems. That was a specific request from a client who has a machine learning system that runs a very large automotive factory. They wanted to understand how can they detect minor changes in the data sets that are actually used to process it. So there's no, we're not talking about malware in the software itself, but actually changes to the data sets that will result in a change in the quality of the systems. So from a signal processing point of view and a macro scale power analysis techniques, we're actually able to create a way to look inside the hypervisor from the amount of power that it's actually pulling and looking at individual tasks and processes, ultimately resulting from changes in data sets, etc. So this is very much my area of passion and interest is looking for interesting and unusual problems. If any of you are familiar with the WARE report, it was a report created and published to the DoD in 1970, and so it's 53 years ago. And it's a slide that I put in every presentation that I do because it still holds true, and 53 years later, as an industry, we're still seeing the same problems. And the fact that it says a combination of hardware, software, communications, physical, personal, and administrative procedural safeguards is required for comprehensive security. In particular, software safeguards alone are not sufficient. And we're still seeing it now. Systems are not designed securely. People are simply trying to patch the vulnerabilities. It's like sticking a Band-Aid on a problem. And I said this is published in 1970, and I think it was made public around the 1990s. But yeah, the WARE report. Now, this is a very simplified version of a sort of systems engineering methodology from a security-specific standpoint. And you start off with any sort of product development. You identify what the need is. You define the requirements. You specify how the system's actually going to operate. You analyze and optimize. You then get to the engineering aspect where you actually let the developers and coders and everything else at it. You then verify and test that what the developers have created actually meets your requirements. Has it met all the test cases? Now, often penetration testing is done often as the product is released or a week or so before it's released, and there is no time to actually deal with it. Now, a lot of our clients actually try and feed the results from a penetration test back into the developers and expect the developers to actually learn something from this. What they end up doing, because they're resource constrained and they have limitations, they try and patch the actual problems. From an engineering point of view, which is the area I focus in, the results from the pen test need to be digested and fed back into when you define your requirements. If there is a penetration testing result, there is a vulnerability, that means somewhere along the line there's a failure in your engineering process. So to make sure that version 1.1, version 1.2 of your product is better and doesn't have this same issue, rather than feeding those results back into the developers, you need to feed it back into the requirements so that anything that flows on from that process is actually improved, fundamentally improved. And other products and other services that you build will start to improve. And this is how we can actually learn from these sorts of problems. Now, a little bit about IOActive. Not sure how much you all know about us, but we are a global company. We've got people literally scattered all over the world. We've got 3 labs, much like this. Obviously this one. I'm not sure if any of you have actually seen the lab itself, but we've got 5,200 square feet of space here, just this little breakout area. We've got a full hardware lab below us. We've got two comms rooms, communications rooms one for dedicated client equipment and one for ours, and secure storage, and obviously the automotive workshop. We tend to focus a lot around industrial control systems and SCADA and OT sorts of things. Our lab in Seattle focuses around silicon reverse engineering, recovering net lists from silicon, etc. And our Madrid lab is absolutely fantastic with fault injection and all those sorts of fun things. But all the labs do very similar things to each other, but we have areas of specialty. And as you see, as a company as a whole, we cover everything from the operating systems through to silicon, through to hardware, reverse engineering, all the way up to the cloud. So pretty much every aspect, full stack, of what you can deal with. And this is, again, a very standard slide that we put in a lot of our decks. Everything is designed, but few things are designed well. And I think it holds very true with what we're showing here. And the reason I came up with this is I've seen what this system is vulnerable to in 5 products in the last few months. Brand new products that clients have asked us to assess and test. And it is concerning that, as far as I'm concerned, these are vulnerabilities that should have stayed in the 1970s, and things should have been learned from these. There's some misnomers that because it's RF, it's difficult. Maybe 30 years ago it was, but anyone with a laptop and a Hack RF1 now can actually do these sorts of vulnerabilities. You can buy that equipment on Amazon. 200 quid, it's not difficult. So a little bit about our history. If you know us from 2015, the IOActive GPAC, focusing around compromising the head unit and taking control of other vehicle systems. You go all the way to the left and sort of early SCADA and RFID cloning. More recently, the SATCOM stuff, medical devices and automotive research, and obviously these sorts of things. A lot of what we do, as you can imagine, is covered under commercial NDAs of commercial in confidence. So there's a lot of things we can't tell you, but we can give you agnostic and anonymized examples about things themselves. So straight into the material that I wanted to talk to you about. This is as simple as it gets, and the reason, again, I wanted to show it is that I'm not saying I'm somebody who doesn't have any experience in this, but I wanted to demonstrate how easy it is, and I'll show you step by step how easy it is to actually identify, characterize, and then actually replay a system like this. And like I said, I've seen 5 systems relatively recently with these sorts of vulnerabilities in them. So this particular example, let's just imagine there's a server somewhere. There's a IP to RF converter, as you can see on the left-hand side, transmits via RF to its sister unit and then down to a PLC. That is basically what I've represented here. So behind you on the left, near the air conditioning duct, there is a small purple cable that goes up to one end of the transmitter rig, and the other end is down here. I've done that specifically to try and get some distance between it, so my radio is somewhere in the middle, so it's more realistic. And what we're actually going to do is just going to sniff the RF data in between and then transmit it. And there's a number of nuances to this, but I'll step through each of those. So this system is vulnerable for a number of reasons. So which parts are actually vulnerable? The application protocol itself. So the actual data being sent from the server and being received at the PLC. Imagine there was a cable. The point 1 is still vulnerable. That protocol in itself is vulnerable. The RF connection itself is also vulnerable. So the RF connection could have a transport layer of security of some sort in there, even if the application protocol wasn't. When we're dealing with the advent of things, fun things such as Industry 4.0, when people are connecting legacy PLCs to the internet with not a lot of actual thought about the risks involved in the application protocols, this is pretty much what you get. You've got a PLC on one side which was never designed to be secure. The protocol that it works on was never designed to be secure. It was always designed to operate on a hardwired network. All of a sudden, we're either sending it over the internet, or in this case, sending it via an RF link, and think, it's going to be fine. So how difficult is a replay attack? And this is where the misnomer is. Unfortunately, it's incredibly easy. As I said, somebody with a Hack RF1 and a laptop and absolutely no knowledge about the protocol itself. What I'm going to show you doesn't require any understanding about the type of modulation, the bandwidth used, the timing of the signals or anything else. It's ridiculously simple. And like I said, there's so many systems that are still vulnerable to this. So let's have a look at why the application protocol itself is vulnerable. You can see up there, this is very much like a standard sort of Modbus RTU protocol. Very similar, or very standard in OT environments. And even when you're dealing with Modbus TCP, it's the same fundamental protocol. It's just wrapped in a TCP transport. But you can see that we've got the various fields, the TID, PID, length, and then some registers. If you look carefully, you'll see that there's nothing that might change apart from the register values, and then you get a response. So you send something to the PLC, either turn something on, give me a value, and then the PLC responds. Nice and simple sort of communication. So in this example, there are two levels of the protocol. Like I said before, there's the server to the PLC, which in this case is Modbus RTU, and then there is the RF communications. In the context of a replay attack, a good protocol should, and now this is according to NCSC, I've added the link there as well. NCSC are doing some fantastic publications recently. They've produced the principle-based assurance model, which is fantastic. It's things I've been talking about and preaching about for years. They've actually gone ahead and created this fantastic material that anyone can reference. But according to their protocol design principles, which is a really good combination of principles people should try and apply, in the context of a replay attack, a good protocol should make compromise difficult, but also make detecting compromises easier. So if we have a look, again, this is a massively simplified message. This is not a Modbus message. This is just for example purposes, so I've simplified it. So we've got command, data, and an integrity field. And for this purpose, that's our CRC16 integrity field. So command F0, for an example, is turn on. Command F1 is turn off. Now what you can probably hear the clicking and the lights turning on and off. What's happening is I've got a simulator which actually controls all of this, sending one command every few seconds, turn this light on, turn that light on, etc., which is very much the sort of format you're seeing there. When it cycles through, and you'll see the same pattern repeat itself, the next time it says turn on, you can see the same message, F0, 87, and integrity field. You can see the two messages are absolutely identical. And the fact that the messages are identical means that these sorts of systems are vulnerable to replay. Much more complex protocols are also vulnerable to replay. They can have cryptographic integrity codes and all sorts of other things, but if they're not implemented properly and they're not designed specifically with replay protection in mind, they will be vulnerable. So let's move on to a nice little demonstration. So what we've got here is, this is as simple as a replay attack looks in RF space. So this is where we're going to capture it. That is my radio source. So just below my laptop here, I've got an ETIS radio B200. You could use a Hack RF1 or a Lime SDR or any of the other fantastic tools out there. I just use this one because that's my standard go-to tool. The power squelch in the middle will allow me to only record when there is actual transmission. So I don't want to record all the background noise. I just want to record the actual transmission. And then we write it to a file. So you can see there's actually only two blocks. It's not much more than a tape recorder, a microphone and a recorder. We're just capturing the signal and writing it off the file. I have no understanding about what's going on. The only key piece of information there is the frequency. You can see it's 443.3 megahertz. Now we can identify that very easily just by looking at an FFT, and you'll see where the spikes of energy are. So that's all I've done. Very, very simple. And I'm capturing 10 megahertz wide. Again, nice and wide. I don't understand. I don't need to understand how wide the signal is. It's in this instance is about 300 kilohertz wide, but I'm capturing a very wide sample. So again, super, super simple. The same approach could be used for a much higher bandwidth signal as well, because I'm capturing so much bandwidth. Then how do we replay it? We retrieve it from a file, and as you can see there, we've got a repeat equals yes. So this particular block will read my very small file and just keep replaying the same signal again and again and again, and then I'm transmitting it. It's kind of scary when you think about the fact that this system is sat there working away very nicely. And I need to explain, I'm not saying that traffic lights use this system. This is a representation of the communication systems, and it's a nice model to demonstrate what can actually happen. There are lots of systems that are vulnerable to this, but for obvious legality reasons, I'm not going to tell you which ones are. But that's how simple a capture and a replay is literally capture the signal, write it off to file, and read it back. So this is what the model looks like, as you can see. So representation there. So I'll change scene. 1 second. Okay, so you can now see that we've got our live camera feed in the bottom left, and you can see the simulator in the top left there, and you can see the lights are actually changing across that. I'll just get this virtual machine running. And for any of you who want to know the password for that virtual machine is password, because it's a virtual machine I share around specifically for this purpose. So let's have a look. We've got the capture demo, which I showed you earlier. Got the source, squelch, write it off to file. So let's run that one. Starting up the radio, just turning everything off. So you can see at the top there, I've got a gain field. So what I've done, when this jumps to life, that's when the squelch is actually allowing the signal through. So I'm just going to record. I'm going to turn the gain up. Yeah, always. Okay, so you can see each time the lights flick, this comes to life. So that's the squelch. I'm only receiving the actual signal. Now the reason why I'm capturing quite a few signals is just to show you that by removing the timeouts in between them. So I'll stop that now. So the replay, I don't think a flowchart can get any simpler than that. We've literally got two blocks, one connected to the other. You can see it's the same file that we're playing, and we'll start that one. Okay, so again, I've set the gain to 0, so the radio is not transmitting even though it's receiving a signal. So I'll just bring the gain up, and you can see all the lights start flashing away. Because all I've done is capture the particular control signals without actually capturing the time in between. And you can see the top right, it's still running away exactly as it was before, but the receiver is getting all sorts of weird signals because all I've done is capture every time it was sending a control signal through, remove the timeout and just started sending it through. And the scary part is the number of systems that are out there, like I said, with these vulnerabilities, and that's how simple it is. Any child who can actually start up a Linux, bare metal Linux or a Linux VM, connect a software-defined radio, can actually do something just like that. And the misnomer that because it's RF, it's difficult, doesn't exist. And because it's illegal, well, we all know that something being illegal stops criminals from doing it. So yeah, the part of the problem is as well, without actually understanding what the data is that you're sending, it's not like you connect to a server and you can talk to it. You just captured something, replaying it. You have no idea what's actually happening. And the range of these signals as well. From this particular radio, I could transmit a signal 5 or 6 miles from here. I have absolutely no idea what I've captured, but I could be transmitting a signal and causing all sorts of chaos. Now, obviously, again, for legality reasons, I'm not. This is a metal building. It's very well shielded and everything stays inside this particular room. So you can see, like I said, as simple as it is, that is a capture and a replay, and we take control of the lights. So we'll go into a little bit more detail. Now this flowchart's a little bit more involved. It really isn't. We've actually got the same radio source. We're still writing it off to file. What we're doing here is we're looking at the amplitude and the frequency, and then we're putting them onto an oscilloscope screen or a time-based sync, so you can see. So we start this one. I'll just disable that. And let this one start up. Okay, so we turn the gain up. Okay, and that's the actual signal that's being sent. So again, if we zoom in and actually have a look, I haven't bothered tuning the filters. I haven't bothered doing anything particular. I've got low pass filter settings and all sorts of other fun stuff I can mess around with to actually clean the signal up substantially like that. Simple as that. That's frequency modulated data. I don't need to understand any of that. It's as simple as what I just did there. Now, I'm not sure if I just overwrote my file, but we will find out to see if it actually overwrote my capture file, which I wanted to show you. I didn't. Thankfully, I didn't. So what I've done here is I actually combined the captured signal for the green light. So I can always force a green traffic light whenever I want to. But what I've also done is I've mixed in a jamming signal. So what we want to do is I turn off the radio. So this is the radio transmit power. We turn that off and it'll continue ticking away merrily. So what we need to do when we're creating these sorts of attacks if there is a valid signal that's coming through, we want to actually create we want to raise the signal to noise ratio so that the noise to signal ratio of the original signal. So this noise is my jamming signal. If I lower jam, you'll see that the jamming signal starts to drop off. See, it actually drops off, and you can see this is our captured signal, and you can see it much more clearly. So if I turn, so that's a 0.7, let's turn that down. Let's put that back. 74. All right, now I'm not transmitting the replayed signal, I'm only going to transmit a jamming signal. IOActive there. And you can now see that it's actually stopped. A little tiny bit's getting through. So one of these signals are very, very close to where we are. I can just increase my output power to jam that. And then if I start bringing my other signal back up, 0.7, 0.5, you can actually start to create a mix at actually where you actually want to create your proper signals. Drop them down to 74. And you can see now I've now got green control of the light. So we've jammed the original signal. Now, in a number of systems that I've looked at, we have two-way communication, two different channels. You can do exactly the same thing. So we've actually had systems sending a heartbeat back. So there's a known state coming back. Well, we've captured one signal, sent one signal, and the head end said, but I'm not getting a valid heartbeat, so what's going on? So then captured the heartbeat signal going back in the other direction, then created two separate jamming signals, drowned out the original signals, and just sent our replay signals. So both ends think they're in full control and think everything's going fine, but we've actually got particular, just packets of data, have no idea what's in them, we don't need to, just packets of data, we can actually control what's going on. Like I said, if I turn off this signal again, just turn the output power off, and it goes back again. It really is that straightforward. So, I've actually got a little bit ahead of myself there because I quite enjoy my radio tools. But I said we can very easily add a jamming signal in on that. And again, jammers, you can come in all sorts of forms. I've just done a simple Gaussian jammer, which is very broad spectrum. You create a pulse jammer. So if you're dealing with state-based communications that actually do some sort of negotiation, a pulse jammer is incredibly difficult to locate and identify, but it's also incredibly effective at disrupting the communication. So you can cause packet loss and all sorts of other fun stuff. And there are tools in here that actually create pulse-based signals and everything else as well. So as a tool, it's open source. It's incredibly freely available. It's installed as standard in Kali, and you just install it in Ubuntu or any other sort of system as well. So as I said, retrieve from file, our jamming signal strength of the main file. This is where we simply mix our jamming signal and get the sort of ratios right, and we transmit. And as you can see, it is literally as simple as it is described. There's nothing complex there at all, nothing clever going on. There really is nothing clever about any of that. So the common solution is, well, how do you prevent replay vulnerability? So let's step back to our original protocol. As you can see there, it's the same slide we looked at before, the message repeating. So a nice simple solution might be to add a freshness value. So let's add a message counter to it. It's fantastic. I've seen this exact scenario. If your message counter, how you handle the message counter and the state, do you just look, it has to be one more than the previous message? In which case, if you jam a single message, then the system loses communication. Well, that's not a particularly good way of doing it. If it has to be at least, it has to be greater than the previous message. Or does that work? Because eventually the counters have to wrap around. So at what point do you decide that, well, it's got to be greater than the message unless it's more than this, and then it can be less than the message. But any of those sorts of systems always introduce a vulnerability. So every single time there is a solution, it introduces a vulnerability. But you can see that by adding a message counter, the integrity field changes. So that, yes, it makes it more difficult, but if the message counter isn't handled properly, or if it's too small, or even if you've got a 16-bit message counter and you're sending thousands of messages a second, you're still going to get a very easy replay every 20 seconds or so. It's not going to be particularly robust against these sorts of things. And if you're sending messages with critical control of power systems, or turning things on and off like this, then you're not going to be sending that many messages. But again, if the message wraps around, a skilled attacker will sit there and wait for the right message. They do understand it all. They'll capture a message and then just keep replaying it. And eventually your message counter will wrap around again. So key here is the protocol handler needs to check the message counter value is always at least one more than the previous value. Like I said, that introduces issues in itself. At what point do you allow the message counter to wrap around? 16-bit, it's only 65,535 values before it wraps around. But there is no authentication or proof of sender. A message like that is incredibly easy to spoof. And I think there's a lot of spoofing vulnerabilities that that some of the big banks try to push on us as well, which I think is a really interesting problem. So definition of spoofing. Now this is something I actually went to Singapore. I was invited by the Singapore Navy to do a presentation to the merchant shipping on how to understand GPS spoofing and also how to detect and prevent it. And it is incredibly easy for pirates, etc., to spoof the GPS constellations when the GPS receivers are not looking for the points of origin. They're not looking for the altitude of the original signals. And you can spoof the signals by spoofing the entire constellation. Again, software-defined radio and GPS spoof constellation spoof is all quite simple. But there is another really common spoofing vulnerability that's all around us every time. And I think a few of you have probably been asked to do this by your bank. My voice is my password. My voice is my password. And it's incredibly easy to reproduce. So I think being aware of the fact that there are messages out there all around us, RF and banks asking us for things that are very, very easy to reproduce and have no proof of authentication or sender. Some of the new messages are looking for ways of proving that somebody is somebody. Don't just send me a picture of you holding your passport, send me you doing a video of you holding your passport. But again, these systems are getting more and more complex, but there's a continuous process around it. So what about more of a cryptographic solution? So let's take our message counter and let's add a SHA-1 HMAC to it, for example. So now we have a hash-based message authentication code. Of course, there are difficulties in implementing this as well. You've got to have an ability to have a pre-shared key. And then manufacturers, including one particular manufacturer, had a hard-coded pre-shared key. And their solution was, well, we'll turn on HMACs and we'll turn on encryption. All the devices use the same key. And that all they were doing was encrypting the message as it stands there. As again, I don't care what's in the message. All I'm doing is capturing the message, completely agnostic of your protocol or anything else, and playing it back. It could be completely encrypted. I don't need to know what's in it. I just need to capture that small amount of time and then replay the message. So the advantage to this is that you can at least have a level of confidence that the message originated, the first time originated from where you're expecting it to, but you absolutely no replay protection. And again, protocol handler needs to check the message counter and support the storage of a pre-shared key. So of course there's replay protection, but what about a hacker solution to that? Then of course, we don't just have simple replay attacks, we then have buffered replay attacks. Now this is where you have complex systems that maintain state between the two of them. And a really classic one is rolling codes inside key fobs. Everyone thinks, okay, they come up with a great way, they maintain state between them, but because these systems aren't actually connected, they have to roll through a known sequence of events. So they have this rolling code. So a buffered replay will capture 2, replay 1. So we'll actually make sure that the first message that you try and send, we capture and jam. So we make sure the receiver never receives it, so its internal state isn't updated. Then typically a retry will happen if you haven't got a return message, or if you've pressed a button on a key fob, you press it again. I didn't wait, press it again. You've then transmitted a second one. We also record the second one, jam the second one, but now replay the first one. So now we've always got one code up our sleeves. So you've unlocked your car, we can now do the same thing. Again, it's not that much more complex than what I've showed you. It is just creating a role. So we keep capturing those messages, using the power squelch, and then we just replay them out of order. So we can always maintain. You create a system that maintains state. We make sure that we're intercepting that state so that your receiver doesn't get updated. So what does it look like? What's a buffered relay attack? So the attacker sniffs 2 transactions, jams the valid signal, but transmits the first one. And it is nothing more complex than what I've shown you here. And this particular example, as I said here, is about unlocking a car. But it's the same basic system that works, and the same state management system that I've seen in a lot of RF systems. So again, you can see the theme here is that there's a problem, there's a solution, there's a problem, there's a solution, and these things keep evolving continuously. Now, I think from a systems engineering point of view, if you step all the way back, the solution has to be specific to what the problem is, what the context is, what it is you're actually trying to achieve. But there are a couple of fundamental things. Like I said, by maintaining that sort of shared state is really important. But if those 2 devices don't have a way of knowing what that shared state should be at any given point in time, like I said, the shared state's all well and good, but if the shared state is transmitted and then the device knows to roll on to the next code, I could hold on to a shared state from 3 months ago. So in more complex systems, how would you actually maintain a shared state? And what should that shared state be? How do you make sure that this message only has a short time to live? So as you can see here, compromise of a message more like this, the HMAC cannot be easily calculated without knowledge of the pre-shared key. So this now makes compromise difficult and provides an ability to detect compromise. So the protocol handler needs to check the message counter is correct. Now, the state field, which I've put up there, how would you actually expire a message? It would need to somehow be related to date and time. Now, if we're talking about these sorts of disconnected systems in unusual locations, you could synchronize them both to GPS time. And spoofing them both on GPS would be an incredibly difficult thing to do. You'd also have to have some understanding of what's in the message to be able to capture the message and then actually spoof the GPS. Now, a lot of GPS receivers cannot be sent backwards in time. They can only ever advance. So you then have a natural protection against this sort of buffered replay attacks on devices which are using GPS state management, because a lot of the GPS receivers will not go back in time. And you can roll them forward, and there's other vulnerabilities with GPS receivers. You roll them too far forward, they can't come back, and all sorts of other fun stuff. But as I've said here, state could be time protocol or GPS epoch, for example, relative date from a particular point. You do end up with issues in the sense that if your epoch is in milliseconds, your message has to be received and processed within milliseconds, so then you have to allow a window. So I'm simply saying there is no simple solution to this, but there are lots and lots of ways to make this a lot harder to do and actually to make it a lot easier to detect that these sorts of things are happening. And if the systems that I'd looked at had implemented something like this, and they certainly had the capability to in both directions, the replays would have not worked. I would have to have gone down a much more complex path of actually having to reverse engineer the protocol, spoof the protocol, understand what was going on, and actually recreate a lot of this, which would have raised the sort of threat level from, like I said, a kid with a laptop and a radio to much more serious researcher or sort of nation state attacks. The concern is that these attacks are real, as you've seen here, but this is just representative. Now, the radios that I'm using are £10 radios from eBay, and the scary part is that these radios have the same vulnerability as some of these incredibly expensive radios that I've seen out there dealing with much more complex things, because they haven't actually thought about what's going over the air. And it's kind of scary when you think these £10 radios from eBay are as insecure as these much more expensive units, which is obviously what this talk's all about. So that was the demo. I'll just change back to the full screen video feed, and then I'll start the so you can see it a little bit. Put it into my party mode replayer. It'll just get going in a second. Radio takes a little while to get up and get going. You can see the lights all flashing away. So nice and short and sweet, but do you because it is a fairly simple sort of compromise on vulnerability. But any questions or anything I can help clarify?